So let's go over basically this is kind of the end of marking period 2 into marking period 3. So let's finish up from the end of marking period 2 here. We're translating this function 4 units to the right. So that means on the inside, if it's going to move right, we're going to subtract 4, because subtracting 4 will actually move it to the right. So positive 3 minus 4 is negative 1. Here we have function notation off the graph again. Again, this is saying when x is 1, what's y? So go to where x is 1, and what's the y coordinate there? The y coordinate is negative 2. Alright, so now we're getting into quadratics. This is a parabola right here. And this question is about an arch. So an arch would have the shape of a parabola, something like that. So they're telling us, asking us what the maximum height of the arch is. Well, that's going to happen at the vertex. Now the x-coordinate of the vertex represents horizontal width, so that's going to tell us how far this way the top is. So when you want to find the x-coordinate of the vertex, you'll do negative b over 2a, which is 3. So we know that this distance right here is 3, but they're asking us how high it is, and that's the y-coordinate, so just plug in 3 for x, and you find out that it's 18 feet tall this way. Then they're asking how wide the opening is. Well, from the end to the middle is 3, so total to get to the other side would be another 3, so that makes 6. The other way to do it is just to set it equal to 0 and solve, because that'll be the other side of the arch, and you can figure out how long this distance is. So here we're shooting a ball off the ground into the sky, and it's shot with an initial velocity of, we can see, 320 feet per second. The negative 16 represents gravity. So when they ask you about the highest point, again, when you shoot something into the air, now it's versus time on this graph here, but the highest point will happen again at the vertex. So the x-coordinate of the vertex is how much time it takes to get to the highest point, and the y-coordinate of the vertex will be how high it goes. So on part A, to answer part A, I actually have to answer part B first. So when I do negative b over 2a, that tells me the amount of time it takes, not the height, but the amount of time it takes to get to the highest point. And when you plug that in for t, that'll then tell you, the output of that will tell you how high it is. So make sure you have that. When you do negative b over 2a, that's how much time it takes to get to the highest point. When you plug that in for t, that's how high it gets. When did the ball return to the ground? You set this equal to 0 and solve, but because we shot this off the ground, it'll take the same amount of time to get to its highest point as it will to get to the ground. But if I didn't shoot it off the ground, if I shot it off the platform or threw it from waist high, then I would set this equation up here equal to 0. And then I would use, say, solve by factoring, quadratic formula, anything like that. Okay. So let's scroll up a little bit. Now we have the quadratic formula. How to use the quadratic formula. Just first make sure that it's in standard form, so everything should be on one side, 0 on the other, the quadratic term, the linear term, and then the constant term. So you have a, b, and c. Remember, a is always the coefficient of the quadratic term. B is always the coefficient of the linear term. And c is always the constant term. If any one of those are missing, then the value of a, b, and c will be 0. So if there's no linear term, this negative 7 wouldn't all of a sudden become b. It's c, it's the constant term, it's the term without x, so it doesn't get like promoted. So just plug and chug here, just be careful, plug in the discriminant in your calculator, and there's 2 answers in one here. Don't forget about that. It's 1 plus the square root of 22 over 3, and 1 minus the square root of 22 over 3. So here we're simplifying radicals with a negative radicand. So that means they're going to be imaginary. So you just want to isolate the square root of negative 1, which will just be I in the end. And then what perfect square goes into 45? 9, and the square root of 9 is 3. So you get 3i root 5. So again, here you have square root of negative 49. So you separate the square root of negative 1, which is I, and then the square root of 49 is 7. Here we're multiplying complex numbers. You're just double distributive property. Nothing changes here. The only difference is at the end, when I get I squared, don't forget that I squared equals negative 1. So I have to substitute that when I have I squared here. So I really get negative 45i minus 6i is the negative 41i. But then when I plug in negative 1 for I squared here, I get negative 18. So 15 minus 18 is negative 3. Our favorite, factoring. So don't forget, step 1 on every single factoring problem is to look for a GCF. After that, you want to consider what size it is to how to proceed. So there's no GCF on number 7. It's a trinomial, a simple trinomial because there's a 1 in front of x squared. So you're just looking for 2 factors of negative 36 that add to negative 5. So if they multiply to be negative and add to be negative, well, if they multiply to be negative, that means they're opposite signs, and if they add to be negative, the bigger one's negative, so that's -9 and +4. Number 8, you look for a GCF. There is none. Then it's a binomial. So ask yourself, is it a difference of squares? Well, it's definitely a difference. 64x squared is a perfect square. 25 is a perfect square. So you get 8x minus 5 times 8x plus 5. Number 9 looks really crazy, but step 1 is just to find the GCF, and in fact, that's all you can do on this problem. The GCF of 10, 15, and 45 is 5. They all have x in common. The smallest exponent is 2. They all have y in common. The smallest exponent is 2. They all have z in common. The smallest exponent is 1. Then you divide each term by the GCF to see what's left inside. Number 10, I look for a GCF first. It's 2. I pull out a 2, and that's helpful because now I'm dealing with a simple trinomial. So look at what's left. It's a trinomial. What multiplies to +10 and adds to 7, 5, and 2. And don't forget the GCF on the outside. Number 11, we look for a GCF. There is none. Then it's 4 terms, so we're going to try grouping. Factor the GCF out of each group, so 2x out of the first 2, a y out of the second 2. Now if you do this right, the 2 parentheses will match out. Basically, I factor out the 3x plus 4, and what's left over is 2x plus y, and that's the other parenthesis. Now number 12, there's a few ways to do it. We've been doing this with the master product, so what multiplies? First I got to multiply a and c on this one because there's no GCF. And I get, ooh, wow, -36. So what multiplies to -36 and adds to -9 would be -12 and +3. So then you would split this middle term. Instead of writing -9x, you would write 2x squared minus 12x plus 3x. Fix that 3. Wow, that's really bad. And then minus 18. And then you would just factor that by grouping, which is how I got to this final answer. Now number 13, you're factoring with more of a purpose. You're trying to solve by factoring. So first make sure that you have everything on one side so the other side's equal. Then you factor it, and then you can just grab the zeros out of each factor. 14, don't forget, step 1 is GCF when you factor. So pull out the 3x, then set 3x equal to 0. You get x equals 0. So 2x plus 3 equal to 0, and you get -3/2. So number 7, we're solving a radical equation here. So just like with absolute value equations, you want to get the grouping symbol by itself. Here I want to get the square root by itself. I know it's really tempting to add 7 plus 3 to start this problem, but this is 3 times the square root, so order of operations says I can't add these. So subtract the 7 first, divide by 3. Now the next step on this would have been to square both sides, but I know that a square root can't come out to equal a negative number, so I know even if I got an answer to this, it would end up being extraneous. So you could stop right here and write that there's no solution. Oh, I think I skipped a page, but that's okay. Well, let's go back over here. So here we're multiplying complex numbers. Again, it's just a double distributive property, and don't forget I squared is -1, so you can just substitute that in. Notice that this problem's quadratic. So it's quadratic, you want to bring everything to one side and set it equal to 0. Here we solve by factoring. You could have solved by the quadratic formula as well. Or because this is multiple choice, you could also always test the solutions to see which pair makes a true statement by both sides being equal after I plug it in. Now we're back to square roots, radicals. Don't forget that on a square root, what you're really looking for is the biggest perfect square that goes into 24, which is 4, and the square root of 4 is 2. Now for the variables, because it's a square root, it has index of 2, you divide the exponents by 2. How many times does 2 go into 14 evenly? 7 with no remainder. How many times does 2 go into 2 evenly? 1 with no remainder. How many times does 2 go into 7 evenly? 3 times, remainder 1. Now the absolute value is because the variables were even on the inside, and if they come out odd on the outside with an exponent, you need absolute value. So number 4, you're just doing a double distributive property. Remember the rule here basically is inside times inside, outside times outside with the radicals. So 3 times 7 is 21. Now 3 times radical 6, one's outside and one's inside, so they just kind of slide together. Technically I'm multiplying the 1 on the outside of the square root of 6 to get 3 root 6. Same thing here with root 6 times 7. You get 7 root 6. Square root of 6 times square root of 6 is the square root of 36, which is 6, and then just combine like terms, which means they have the same radicand. Number 5, I'm looking for the biggest perfect cube that goes into these numbers because it's a cubed root. 8 goes into 24, cube root of 8 is 2, and then I multiply it times the 5 that was on the outside already. Biggest perfect cube that goes into 81 is 27. Biggest perfect cube that goes into 192 is 64. Then at the end, because they all have the same radicand, I can just combine like terms. Number 6, I'm solving again a radical equation. This time it's cubic. So again, it's tempting to do the 9 minus 2. I'm not allowed to. Order of operations. Subtract 9 from both sides, then divide by negative 2. I don't have to worry about the rule with the negative on cube roots because cube roots can actually come out to equal a negative. Cube both sides. Cube just cancels out the cube root on the left side. Then you subtract 3 from both sides, and x equals 5. Alright. So we already did number 7. Let's do number 8 now. Find the inverse. Remember, an inverse just undoes the original. So g of x is the same as y. So what I want to do is flip the input and the output. So flip the x and the y, and then try to solve for y. So first thing you would do is divide both sides by 3, then square both sides, and then add 5 to both sides, and there's the inverse. A little more factoring. Number 9a, you're just looking for a GCF there. Pull out the GCF, 4xy squared, and there's nothing else you can do with what's left. On B, pull the GCF out, which is 2. If I look at what's left, it's a binomial, and it's a difference of squares, so that factors into x plus 2 times x minus 2. On C, pull out a GCF of 2, then 2 factors of negative 10 that add to positive 3 are positive 5 and negative 2. Here we got no GCF, and A isn't 1, so I got to do A times C is 15. 2 factors of positive 15 that add to negative 8 are negative 3 and negative 5. So then I would split the middle term and have 3x squared minus 3x minus 5x. Excuse me. This is not very good for numbers. Minus 5x plus 5. And then I would just factor the rest of that by grouping. Number 10, we're solving an inequality. The main thing to remember when you solve an inequality is that if you end up having to divide or multiply both sides by a negative number, the inequality sign flips, and that happens right here when I divide by negative 3. The inequality sign flips. Now when I graph this, remember it's or equal to. So I use a solid circle, just like if it were a linear inequality, I use a solid line, solid circle, solid line, and where the number is less than or equal to 13 from here over. Again, absolute value, we're trying to solve it, so isolate the absolute value, subtract 6. I get the absolute value equals negative 4. Absolute value could never come out to equal negative, so at this point you can tell that there's going to be no solution. Number 12, I isolate the absolute value again by adding 5 and dividing by 3. And again, there's two cases, the positive case and the negative case. So just set it equal to 4, set it equal to negative 4, and solve each one. Number 13 is an absolute value inequality. So still two cases, positive case, negative case. But on the negative case, I also have to flip the inequality sign. You also want to remember this is a less than sign, so this is an and problem. So you're looking for the intersection of those two inequalities. And if it was a greater than sign, greater, it would have been an or problem. So we're looking for the intersection. Where are the numbers that are both less than or equal to 7 or greater than or equal to negative 2? Right in the middle. Let's scroll down to the last page. Here's a greater than sign. Again, still two cases, the positive case, the negative case, flip the inequality sign. So this is an or problem, and since it can be either or, that's why I just get both outsides. If this were like an and problem like this, the answer would be no solution. 15 we're solving by factoring, so bring everything to one side, factor, and then grab the zeros. 16 you're using the quadratic formula, just make sure everything's on one side, grab A, B, and C, plug them in, and there's two answers in one here, 7 plus the square root of 33 over 8, and 7 minus the square root of 33 over 8. So, and last but not least, we got the last one here. Oh, one more page after this. No, this is it. 17. Completing the square. Alright, you gotta know how to do this. So the first thing I want to do is isolate this constant term. So I add 1 to both sides. Now, I want to take b over 2 squared on both sides. So I want to do negative 10 divided by 2 squared. So that's a negative 5 divided by 2 squared. Oops, sorry, just negative 5 squared. Not negative 5 divided by 2. And that's 25. So you add 25 to both sides. That's here and here. Oops. Here and here. So on the right side, 5 squared is 25, plus 1 is 26. Now on this side, remember, there's a shortcut to help you factor. Whatever b over 2 was is what it's going to factor into. So this factors into x minus 5 squared. Then I just take the square root of both sides, don't forget your plus or minus sign, and add 5 to both sides. So that's a little review of the second and third marking periods.